So automated detection of automated traffic. The problem I want to talk about is you have a web service which attracts human traffic, which you want, but it also attracts bot traffic, which scripted automated behaviors from bots which try to abuse the service and are not what you intend. A good example would be something like sign-up abuse, where we want people to sign up for Hotmail accounts and Gmail accounts and Facebook accounts and stuff like that. But we do not want the bots that try to sign up for tens of thousands and hundreds of thousands of accounts and just abuse the service. And other examples are, fake engagement on social media, click fraud, and stuff like that. Now, the problem is challenging for a couple of reasons. One is there are no labels and there will be no labels. I mean, we have to make our peace with that fact. And that means that all of the supervising learning algorithms that we know about, logistic regression and SVMs and neural networks and all that great stuff, and great stuff it is, but it's off the table. We simply can't use it. We don't have labels and we're not going to get labels. Equally troubling is that most of the unsupervised algorithms that you might know about, like k-means and clustering methods and isolation forests and stuff like that, most of these things rely on taking numeric features as input. That is to say, they expect inputs which are vectors of floating point numeric features. We don't have that. What we have are categorical features. If you're looking at weblogs, your browser version is a string. The geolocations such as state or city or something like that is a string. Refer, user age, and stuff like that, these are strings. So we don't have numeric inputs. So basically, all of the good unsupervised methods are all kind of off the table also. And then finally, the stuff you might try, anomaly detection, sort of relies on the heuristic that your historical distribution might be assumed to be mostly good, and that the bad stuff that you're going to see are rare outliers that deviate significantly from your historical distribution. That's not even approximately satisfied here either, because for many of these problems, like sign-up abuse and like click fraud and stuff like that, the levels of abuse that we expect to see could be 10%, they could be 30%, they could be 70% of our overall traffic. So relying on a heuristic that most of what I see is minor deviations is not a good heuristic. So what I'm going to try to do is I'm going to try to estimate the clean distribution and then punish deviations from it. So imagine, for example, that bad guys took a day off and there was no attack traffic during that day off. Well, what I would do is I would snapshot all of my distributions during that time, learn the clean distribution, and then when bad guys come back, punish deviations from that known clean. So writing it here as, observed is equal to alpha times clean plus 1 minus alpha times bot, where my features are x and y. If I knew what clean was, then just some moving things around, the odds of any particular thing being bot is just given by this right-hand side over here, observed over clean minus 1, basically. And I could output a set of rules that tells me for any given observation what the odds of being bought are. Well, of course, that's not going to happen. Bad guys are not going to take a day off, and we're not going to be able to, get the clean distributions in a nice, easy way like that. But suppose, however, I were able to identify subsets of traffic which were fairly free of attack traffic, and I were able to estimate clean from that. So here I'm going to introduce the two main assumptions in this paper. One is that I have pairs of features, x and y, which are independent, statistically independent of each other. A good example might be, say, browser version and geolocation. Within the US, I expect the location in the good traffic of, let's say, browser version in Oregon to be the same as it would be in Georgia or Iowa or anywhere else. I don't expect that changes in the clean traffic all that much. That is to say, Chrome is not that much more likely to be used by people in one state, versus another. And the second is that in one of those features, let's say state, I can that there are unattacked bins. There are some bins that receive 0 or negligible attack traffic. So, for example, if in 50 states in the US, suppose, for example, Oregon is unattacked. Well, if I plug that in, that would allow me to calculate the clean distribution. That is to say, my observed here is equal to alpha times clean plus 1 minus alpha times bot. If Oregon were unattacked and I evaluated this equation for Oregon, well, this bot term here simply drops out, and it tells me that observed is simply equal to the clean. So I get the clean distribution from the observed distribution if I'm staring at a bucket that is unattacked. Okay, that's nice. That feels like the beginnings of progress. Okay, but two questions before I go any further is, A, why would there be unattacked bins, and B, how would I find them? So in the first of those, if you look at, say, a feature like state, Well, attackers might have a lot of bandwidth and attack traffic coming from states like Virginia and California and places like that where they have a lot of bandwidth, where there are AWS and Azure data servers and stuff like that. But they don't necessarily have coverage in all 50 states. There might be places like West Virginia and Iowa and who knows what else that are relatively unattacked. So this is, unless they have coverage across the entirety of your space, the first assumption is met. So how would we find those buckets? I mean, even if Oregon is unattacked, it could be staring at the distribution, but I wouldn't quite know it. And let's get to that next, which is, okay, as I said, if Oregon is unattacked, it gives me the clean distribution of browser in that bucket. Well, suppose I had more than one bucket that was unattacked. Suppose Oregon and Iowa and Georgia all received no or very little attack traffic. Well, then all of them would point to the same distribution. They point to the clean distribution. There's only one clean distribution. Since they're all unattacked, they're all pointing at the same thing. The central result of this paper is basically that the converse is also true, is that if I have multiple bins that are pointing at the same distribution, they're pointing at the clean distribution. That is to say, if I find that the distribution of browser version in Oregon and Iowa and Georgia are the same, believe it or not, that is the clean distribution that you're looking at. It's stated a little more formally. It's stated a little more formally in the paper, but basically, and there's no real additional, strong assumptions there. The only assumption is that the traffic distribution from the bot traffic is not the same as the traffic distribution from the clean traffic, which if it were, you're kind of done anyway. So basically, this gives me a mechanism to find the clean distribution by finding marginals that point to the same thing. A matrix representation of this kind of gels well with the implementation, so let me just do that. So let's, instead of writing it in algebra as I did before, write it as a matrix, the joint distribution of x versus y as a matrix, and on the left-hand side, that would be what I observe, and the observed is equal to alpha times clean plus 1 minus alpha times bot. The xy, the distribution matrix observed is equal to the distribution matrix of clean plus the distribution matrix of bot. Now, the distribution matrix of clean as a matrix, this is rank 1. Why is it rank 1? Because remember we said x and y are independent, and that's what independent means. The rows and all the rows and all the columns of that matrix are going to be linearly independent. But what you observe is not going to be rank 1 because it's contaminated by this other additive component, which is the distribution matrix of the bot traffic. Now, if we do have unattacked bins of this from bot traffic, how that would show up in the matrix notation is this x times y distribution matrix of the bot traffic will have some columns that are purely 0. And what that means is that while this overall observed matrix is not rank 1, it does have some subset of columns that are rank 1. And again, it's stated a little more formally and algorithmically in the paper, but to skip right to the punch, the distribution of x in clean is given by the span of the largest rank 1 subset of columns of that observed distribution matrix. You just take a pivot matrix of x versus y, and the clean distribution of x is the span of the largest rank 1 subset of columns that you can find. Written in pseudocode, it goes something like this. This first routine here, get cleans, is this is to find the clean distributions, and it just loops over all of the features that you're interested in. Suppose I have a set of features, W, X, Y, Z, whatever. I loop for F in every one of those features. Form a pivot table for F, which is where F is the index, and the columns are all the bins of all the features that are statistically independent of F. And then find the cluster of the largest cluster of linearly dependent columns that you can find. That's your clean distribution. And then using the clean distribution is simply a matter of pushing through that odds ratio that I gave in the beginning. The odds for any particular observation is the observed divided by clean minus 1 for any observation. And overall, the whole thing is just take something, for example, a set of weblogs in, run it on this algorithm, and then the output is the estimated odds of being bought. So if my features here are country, state, browser, and organization, or something like that, it'll output floating point numbers that are the estimated odds of being bought. Okay, So then to evaluation. As I said, labeled data sets in this space are extremely rare. As a matter of fact, they're almost unknown. We're lucky to be able to find one set of web server logs from 5 years worth of logs from a smallish site that publishes their server logs, but also interestingly publishes their manually curated firewall decisions. So we actually have a proxy set of labels from the firewall decisions that can lead us, at least for evaluation purposes, as to what, whether we're going in the right direction or not. And this would give us an underestimate, meaning that the firewall probably didn't capture everything. So our ROC curve here would be. This is the strictly worst RSC curve that is possible. But long story short, using 4 features, browser, family, status, and the path of the requested file, the area under the curve that this algorithm finds is 0.087, and that's the black curve here, and isolation forest, which is a very kind of prominent unsupervised method, essentially does not do better than random. A second evaluation I did on a Twitter data set. I was fortunately to find 2 Twitter accounts which self-advertised that they had purchased bot followers in certain amounts at certain times. And again, we were able to use this as a mechanism for evaluation. Again, with a fairly small set of features, just five features here for these 2 particular accounts. Black is the ROC curve produced by this algorithm. Green is produced by Botometer, which is a Twitter bot detection mechanism put out by Indiana University that has an open API. And then again, the blue is isolation forest, which is one of the prominent unsupervised methods. And the point here, I guess, is not that necessarily that this is the best classifier you've seen for any task ever. The area under the curve is about 0.8 here. But given that none of the supervised methods that we know work at all, and the unsupervised methods basically don't do better than random, this is essentially the best that we know how to do. And then we also evaluated on a crawl of 5 million Twitter accounts crawled using the public API. Unfortunately, there we have absolutely no labels, so we don't know how we can't draw ROC curves or give precision recall numbers or anything like that. But we still went through the exercise, calculate the cleans, and then look at the rules that are generated and look at the things that are most likely to be bought. And so it is possible, and I'm not going to go through all of the examples, but the paper gives quite a few examples of cluster behavior that are clearly evident. Here is the top one of the rules that is output saying that features accounts that match this particular configuration of features have an odds ratio 700 to 1 of being bought. And when we look at that in a little more detail, there were 400 accounts that met this, and every single one of them had this kind of naming pattern where their alias, the username chosen, was a last name plus 2 letters plus 2 digits. And when we examine those 2 letters and those 2 digits and use a chi-square test, they're structurally random, right? They are, they are uniformly distributed across the entire space. So there's absolutely no possibility whatsoever that these were generated by 400 independent human beings. And in the interest of time, then, let me just skip to the end to the conclusions and say, basically the main mechanism here is when X is independent of Y, you can get the clean distribution of X by finding this span of rank 1 subset of linearly dependent columns of Px of Y. It's unsupervised, categorical features, and a really nice property of this thing is it's kind of one-sided. I'm not doing anything to learn what the bad guy is doing. The bad guy can vary all he's want. And in particular, I'm not assuming that the bad traffic that was observed in training is going to be representative of the bad traffic that is going to be seen in deployment. I'm not making any assumption like that. Okay, let me end there. Thank you.